everyone, and welcome back. My name is Mr. Cobalt, and in this video we're going to talk about and we're going to compare the orbital energy level diagrams for hydrogen, which is a one electron system, to other atoms that have more than one electron. What is the difference and why? So let's get into this. So first, let's read the question. So it says the relative orbital levels for the hydrogen atom can be represented as shown in the diagram below. What diagram are we talking about? This diagram right here. So here we have the energy levels of the hydrogen atom. So remember, hydrogen only has one electron, and so this is the energy levels. This is how they look in hydrogen when you only have one electron. And this would be true for any electron system, any atom that only has one electron in it. The energy levels are going to be organized in this way. So you'll see the 1s is lowest, and then you'll see the 2s and the 2p sublevels are at the same energy level. And then you'll see that all of the energy level 3 sublevels are all at the same energy level. And then we could continue with 4 and 5 and so on, but this is enough to get the idea. So this is what the energy levels look like in an atom like hydrogen that only has one electron in it. Okay, so let's continue with the question. It asks us to draw the relative orbital energy levels for atoms with more than one electron and explain your answer. Also, explain how the following radial probability distributions support your answer. And what are these radial probability distributions? That's these right here. So what they're showing you is the probability, the radial probability of finding an electron close or at some distance to the nucleus. And so when you see the diagram, this plotting of the probability, it's like a probability map of where you're going to find the electron. Where are you most likely going to find the electron? And the most likely place that you're going to find the electrons are at the peaks. So you'll see here with the 2p orbital, this is the radial probability distribution map for the 2p orbital, and you'll see that the highest probability of finding the electron in the 2p orbital or sublevel is going to be at this distance here. And you'll see at the 2s that the radial probability distribution, you have two peaks. So you have a peak here. This has the highest probability, but then you have a high probability of finding the electron here closer to the nucleus, right? So I'm just explaining how you would read this sort of radial probability distribution map. So you can see that here. And then over here we have 3D, 3P, and 3S. So this is the radial distribution map of what you would see for a multi-electron system. This is for more than one electron. This too is also, if you have more than one electron, this is what the probability distribution maps look like. Okay. So when you have the 3D, the 3P, and the 3S here, so you'll see that for the orange color, that's the 3D, you only got this one big hill or hump here. And so the largest probability of finding the electron in the 3D is going to be this distance from the nucleus. So again, this is distance from the nucleus. So I could write that here. So distance from nucleus. And again, this is radial probability. So again, radial probability. So for the 3D, this is the highest probability that you're going to find the electron is going to be this distance from the nucleus. For the 3p in blue, you got, again, 2 humps here, so you have a high probability at this distance from the nucleus. And then you have this other probability that is here. You have another maximum probability here. So you have a high probability of finding it here as well. And then you have, for the 3s, you have 3 humps. And you can see that here you have a third hump that's even closer to the nucleus. So these are the probabilities of finding the electron in the 3s at a certain distance from the nucleus. Okay, so that's the way you understand or you read these probability distribution maps for the electron at a certain distance from the nucleus. Okay, so we got a couple of questions here. It says, or a couple of things to do. First, we want to draw the relative orbital energy levels for atoms that have more than one electron. So the thing you got to remember for electrons or atoms that have more than one electron is that once you start throwing other electrons in there beyond one, you now have repelling forces. When the electron is by itself, the only interactions, the only forces that are there are the attractive forces between the electron and the nucleus, right? So you don't get these repelling forces that get in the way or interact. So, but when you throw another electron in there or more electrons in there, now you've got these repelling forces that are going to change things, right? And so these repelling forces are going to cause what we refer to as orbital level splitting, right? So you get this splitting of the orbital levels, and they're no longer going to be at the same energy level. So if I was going to write this down, the 1s would still be first on the bottom, so we'd have the 1s. And then next would be the 2s. But because of the orbital splitting, the energy level splitting due to the electrons now occupying, different spaces, or at least occupying the same space, they're now going to have these repelling forces, excuse me. And now, because of those repelling forces, you're going to have this shielding effect, right? So shielding effect can now occur. And so the 2s over here, the 2s and the 2p are at the same energy level. Over here, they're no longer going to be at the same energy level. So they're going to be a little bit higher. So now you got the 2p, which is going to be a little bit higher than the 2s. And then you come to the 3s, which is going to be higher than the 2p. But here, remember, when you only have one electron, like hydrogen, you're going to, all of the 3 energy level 3 sublevels are going to be at the same energy level. So the 3s, the 3p, 3d are going to be at the same energy level. There's no energy level splitting. And so here, when you have more than one electron, now you're going to get that energy level splitting. So the 3p is going to be higher than the 3s, and then the 3d is going to be higher than the 3p. Let me move this over so I have room. So I'm going to write this 1, 2, 3, 4, 5. That's the 3d. So now you get this orbital splitting, this energy level splitting due to the interactions of the electrons themselves, this repelling force. So not only do you have the repelling force, but you also have the attractive force of the nucleus. So there's kind of a tug of war or a contrary forces going on here. So you have the attractive force that's of the nucleus attracting the electrons to it, but you also have the repelling forces of the electrons pushing each other away. And so that's going to cause the energy levels to no longer be at the same equal level, right? So this would be the expected energy level of the energy levels of the orbitals and the sublevels when you have more than one electrons. Okay, and so this is also going to be due to some penetration going on here, right? So you have the shielding effect, right? But you also have penetration by different energy levels. Different orbitals or different sublevels are able to penetrate closer to the nucleus than others. And again, depending on how closely you're able to get to the nucleus, that's going to cause a lowering of the energy level. Because remember, the closer the electron is able to get to the nucleus, the lower the energy. So depending on what orbital or what sublevel you're in, if you're in a P or an S or a D, that's going to involve more or less penetration into or closer to the nucleus past the shielding, right? So that's what this is showing here. So again, so we're getting into the next question. It says, also explain how the following radial probability distribution maps support your answer. Well, so here we see that the 2s orbital or sublevel is lower in energy than the 2p sublevel. So is this supported by the radial probability distribution map for those two? So here we have the 2p and the 2s, and you'll notice that the 2p here, it's close to the nucleus, and then as you get farther away, it spikes up to this level here. So you have a maximum probability of finding the electron at this distance from the nucleus. And then it tapers off at lower probability. So the probability goes down as you get farther away. Okay. Now look at the 2s. Notice the 2s has a large probability at a farther distance, right? So you would think that all things being equal, the 2s would be farther away than the 2p. But notice here you have this little peak here. So you have a relatively high probability of finding the electron at this distance from the nucleus. And because you have that little peak there, you have a higher probability here than here, right? So the 2s, and this is what we refer to as penetration, the 2s electron, the electron in the 2s sublevel or orbital is able to penetrate closer to the nucleus compared to the 2p. And because it can penetrate closer to the nucleus, then that gives it a lower energy, right? So closer to the nucleus means lower energy. So the 2s is going to end up having a lower energy than the 2p because of that penetration into the inner sanctum or inner part of the atom. So remember, you have the 1s electron, or the electrons in the 1s orbital are kind of shielding the nucleus. The 2s and the 2p can penetrate past that shielding and get closer to the nucleus. The 2p here, they're the same energy, but here, because the 2s has more penetrating power closer to the nucleus, it ends up having a lower energy compared to the 2p. And so this radial probability distribution map supports this being the 2s being lower than the 2p. And then if we look at the 3s, the 3p, and the 3d, we see the same thing over here. So again, as I pointed out, the 3d here has this probability map in orange. So you'll notice that 3D is highest of these two. If we look at the 3P, you'll see that in blue, the 3P has one peak farther from the nucleus compared to 3D, but it has this little peak here. Notice that the peak here is closer to the nucleus, and because of this penetration by the 3p electrons, they're able to get closer to the nucleus than the 3d, thus giving the 3p sublevel, those electrons, a lower energy. And then you'll notice here that the 3s has lower energy than the 3p. If you look at the green line here, you have one peak here. That's going to come down, and then you have a second peak. So the second peak is still closer than the 3D, but then notice that it has this third peak here closer than the 3P. So because you have that little peak here, it has a higher probability closer to the nucleus than the 3p, and therefore the 3s now has a lower energy than the 3p. So again, it's because of the 3s and the 3p are able to penetrate closer to the nucleus due to these higher probability peaks over here that they are going to have a lower energy than the 3D, and the 3s is still able to penetrate closer than the 3p, so it has a lower energy. So the closer you're able to penetrate, the more you're able to penetrate closer to the nucleus, that's going to allow you to have a lower energy, because again, as you get closer to the nucleus, the electron lowers its energy. And so we see that depicted here in the radial probability distribution maps. And so that explains why you see this when you have more than one electron, but you don't get that when you only have one electron, because you don't have any shielding, you don't have any penetration going on. It's just a one electron, right? So when you only have one electron, that one electron is just going to be in the 1s. So there's no penetration going on. There's no shielding going on. But as soon as you start throwing more electrons in there, you get that repelling force. That repelling force allows for shielding. Okay, and then that causes the orbital levels to change. They're not going to be at the same level anymore. I hope this is helpful. If this made sense, I'm glad. If it didn't make sense, if you enjoyed the video, if this helped you in any way, then please like the video, share the video, hit that like button somewhere over here, maybe. Also, do me a favor, please help me out. Subscribe to my channel, hit that notification bell. When you do, make sure you click all. When you that way you'll be able to get all my videos. You'll get the notifications for all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, put that in the comment. If you have a topic you want me to cover, put that down below in the comment. I would love to do that for you. Thanks for joining me, and have a great day.